Okay, so good evening, everyone. We'll start with today's problem solving session. So I'll just go through the things that we have covered till now in the control engineering lecture series. So what we have learned till now is first we saw what are transfer functions, Laplace transforms, how do we do that, the properties and all. Then we looked at some systems, how to get transfer functions or models of systems. We saw some physical, mechanical and electrical systems. Then we came around to studying stability via the Rautare criterion. And then we learned some time domain and some frequency domain techniques to get a better qualitative and a little quantitative information about a given system and essentially study how relatively stable it is. That is the main idea behind studying and analyzing the systems that we have been doing. That we want to see whether this won't blow up or cause any harm, and if this works the way it is desired to in the real world. So today also we'll do a mismatch of whatever we have done till now and try to apply those techniques into our current analysis of the questions that we have for today. So with that we'll start. So now we are being given this system. Consider a system with a closed loop transfer function given by this. So this is the closed loop transfer function. So where are the zeros? Zeros are at two repeated zeros at alpha and poles are at, we have three poles, and this seems like a stable system. We can also check using router. But for this question, what we want to know is for alpha greater than 0, the system is which kind of system? So is it a minimum phase system? Is it a non-minimum phase system? Or is it an all-pass system? So would you like to guess which kind of system this is? I'm sorry. Yeah. So would you like to guess which kind of system this is? Okay. So what a minimum phase system is, it such a system must have all its zeros and poles in the left half plane. So that is a minimum phase system. But here, if alpha is greater than 0, then we can see that there are two zeros in the right half plane. So this is a non-minimum phase system. Alright? And an all-pass system is essentially, it will have a magnitude of 1 so that it will pass all, like the magnitude will be independent of the frequency. So that is basically like, suppose we have a system like s minus 2 by s plus 2. Then when you find out the magnitude, it is root omega square plus 4 by root omega square plus 4, right? So here the frequency terms cancel out and what we are left is the constant. There could be some gain multiplied here that might remain. But the frequency dependent magnitude terms of the entire transfer function would be non like sorry, the magnitude of the transfer function will be independent of the frequency terms. So that means every frequency that comes in will pass, like it will pass via some constant gain k or 1 or whatever it is. So but suppose you have something like say 1 by s plus 2, then what is this? The magnitude is omega square plus 4. So here you can see that the magnitude, the gain via this transfer function, this is the transfer function, so j omega, this gain will go to 0 very quickly as omega goes towards infinity, right? So what that means is after a certain threshold, the frequencies after a certain threshold, they'll start dipping down. So we'll have something like this. So this is some kind of a low pass filter. That is, will pass only the low range of frequencies. So, but in an all pass system, there are no frequency dependent terms in the magnitude. So all frequencies pass without any distinction. So that is why it is named as an all pass system. But for this one, that is not the case. We have only two zeros on the right half plane, so it is a non-minimum phase system. Is it clear? Okay. So we'll move on to the next question. When a unit step input is applied, how many zero crossings occur in the system response if alpha greater than 0? Right. So we have the same thing. Ys by Rs is equal to S minus alpha square. This is the transfer function. So what do you guess the system response would be? Like, why do you think there should be zero crossings? Okay. So now let's just take this system. And okay, let's take alpha is equal to some 2. Right. So for this system, what do you think? Will there be any zero crossing? Okay, let us check it with MATLAB. Can you see the font? Yeah, okay. So, just a minute. Hmm. Yeah, so now what we had the transfer function. Let us take g of s, g is tf. Right. So this is our transfer function. Sorry, this is just the denominator of the given transfer function. Okay. The s cube plus 6s square plus 11s plus 6. Now let us see what will be the step response of this. So, yeah, can you see the screen? Yeah. So do you see? So how is this plot? Like we can see, it starts from somewhere around zero, like at time zero, it is at zero. Slowly it goes up and then settles at the whatever the steady state value is. All right. So we see no overshoot, undershoot, nothing. Now, what will happen? So let us take. Okay, now I'll share my writing pad again. Share screen. Give me a minute. Yeah. So now this thing, not this thing. Basically, x of t will take RFS as 1 by s because we took the step input. So x of t, whatever we found out, it was something of this sort, right? Something. There were no undershoots or overshoots, whatever they may be. Now we are concerned about zero crossing. That is whether this will happen or not. Whether it will come down or go up and do things like that. So for that, let us take let us consider this thing as x of t, right? Now consider y1 of t, y1 of s by r of s as s minus alpha 2 by that thing, s cube plus 6s square plus 11s plus 6. Right. So here, do you have any idea what kind of system response you'll get if you give a step input? Okay, let's see. Yeah, yeah. Okay. Okay, so let's see. Y1 of s is just s into r of s. Oh, sorry. Now we saw that r of s into this denominator term is x of s, right? So this is s minus t into x of s. So that means s x of s minus 2 into x of s. Is that correct? So now if you take the inverse Laplace, what this means is we have something like this. Is that correct? Do you follow what we did here? Yeah. So what we are saying is this: when we add a zero, the new response of the system in terms of this x of t, that is only with the poles of the system, no zeros. What it will be is it will be a function of that x dot and some x, some constant, whatever, x of t. So what this means, so here you can see in this part x is increasing, so x dot is definitely positive. But here perhaps early on, if you see, the increase is not that rapid. So x dot is a small quantity. X dot small. But at that time, x of t seems to be larger than what the rate of change is. So initially what might happen is we might get an undershoot. Okay. Since there is a negative multiplication term, let's again check it with MATLAB. Okay. So now I'll find out y1, let's say g1 is 1 minus 2. Right, so this is the transfer function we want to check. Let's check its step input now. Okay. So can you see the step input now? Yeah, it is set at some negative value. Perhaps when we'll put the, yeah, you can see the original system was, hold on a minute. Yeah, the original system, if you remember, where is that? Yeah, it is s minus 2 by something, something, something. So when we find the steady state value, limit s goes to 0, s into 1 by s for step input into this g1, then we can see that only remaining thing will be minus 1 by 3. And this thing actually settles down to minus 0.33 something. So it works. But here you can see, so yeah, due to that subtraction x dot minus 2x, we get something like this. Okay. Now the next step we can choose is we can next take s minus 2 d2 is a minute. Okay, so this is the original system that was asked to us in the question. Now let us check this thing, right? So now what do you see? Now you can clearly see from 0, it goes on upwards, then comes back down, then again crosses everything to move back to some other steady state value. Okay, is this clear? I see we got some new people in. I'll just, yeah, that's true. So the thing is, you can make a guess from the questions. I'll get back to my writing part. 1 minute. Yeah, yeah, I'll just go through the things again. Yeah, okay. So we were given this system, alright. This system. We want to see when a unit step input is applied, how many zero crossings occurs in the system response. Alright. So we are taking a dummy value, let's say alpha equal to 2. Then what we did was, let us take a look at this system. That is only with the poles of the given transfer function, no zeros. Then what do we have? So this thing when we plot, okay, let me just go through this. So the question given to us is this system. This system is there. We want to apply a step input and we want to know how many zero crossings will occur. Well, why would a zero crossing occur? Usually for all second order systems, we know we have something like this. But for different kinds of systems, we might have things like this, say, well, not like this, but say like this. Then these points here, they will constitute of the zero crossing. Alright. So we want to see if it happens in this case, right? Then alpha equal to 2 will take this example. Then now just consider the system given by the poles and just remove all the zeros. X of s by r of s. So how would this kind of system be? Any guesses for those who weren't earlier? Okay. So actually, see, whatever questions you'll get in exam, it will be such that you can compute them. Like here, it is a third order system, so then you'll have to find out dominant poles, do some calculations and things like that. But I don't think those kinds of questions will come in exam. Like here, we are just learning how to approach these problems. That is why I'm using MATLAB more frequently. But in exam, you'll get things that can actually be solved with hand and whatever calculator provision you have on that online thing. So don't worry about that now. Let us just look at how we'll get, like, how to actually think about these kind of problems. So I'll share my MATLAB. Yeah. So, okay. So you can see that we took this transfer function that is only the poles of the thing, no zeros. Then G1 is the transfer function with 1 0 and G2 is the transfer function with 2 zeros, right? Let us just take the step functions and look at it first. So yeah, can you see this like step response? So here we can see that the system with only the poles, no zeros, that gives us kind of a system response that we expected. It will start at 0, then go upwards to its steady state value. Maybe have some overshoot, may not be. Here it doesn't have, and then goes to the steady state thing. So now, but when you see for G1, that is the system with 1 0. Now there is something quite peculiar here. You can see that there is one kind of overshoot from 0. Then the system comes back, crosses 0, and goes to some negative steady state value. Right. Now further, if you look at step response of the system with 2 zeros, now it is even more peculiar. Like, why is this happening? We start at 0, we go above a little, we hit a peak, then come back down, we hit a trough, then again go back up and settle at the steady state, at some steady state. So here you can see there are two zero crossings, right? Yeah. So there are two zero crossings, one somewhere here and the other somewhere here, approximately at times 0.873 and some 0.375, right? So why is this happening? So for that I'll come back to my writing pad. So I'll just erase the things for now. Okay. So we saw that with R of S is equal to 1 by S, the X of t we got was something like this. Is that right? So here there are no undershoots. Now let's see what would happen if we have this system. This is the G1 that we took in our figures in the MATLAB thing. So then you can see that y1 of s is nothing but s minus alpha into x of s. Is that correct? Now this is just s into x of s minus alpha into x of s. Now if you take the inverse Laplace transform, we'll get something like x dot of t minus alpha is 2 here, 2 into x of t, right? So is it clear till now? Is this part clear for everyone? Yeah, okay. So here you can see, so look at this. As the here clearly the value of x is increasing, it isn't decreasing. So this part is positive, that's for sure. And this part, x of t, is increasing very slowly, but it is increasing. So that is also positive here, right? So what happens is, then you can check the steady state value of y1 of t. That is limit s goes to 0, s into y1 of s, right? So if you check that, you'll get something minus 1 by 3. Okay. So that means for y1 of, okay. So we had x of t as something like this, settling to some steady state. Now we want to analyze how would this be, right? So say we computed x of t, alright. Then we can check x dot of t at some very small t value, say 0.01, alright. Then at that value, you can check x of t, 2 into x of t at t equal to 0.01. Then you can compare these two. So my bet is it will be x dot of t is greater than 2x of t for t less than some t naught. Alright. But now limit s goes to 0, s into y1 of s is negative. We can find that from using the final value theorem. So what will happen is, initially there will be some part where y1 of t is positive because this case is true. So it will go up, then it will come down and settle at the negative value. So that is what we saw in the actual step response when we plotted it in MATLAB. Is it clear till now what we did? Okay. So similarly, then we'll go forward with the analysis, and actual y of t will be s into y1 dot of t minus 2 y1 of t. Now see that y1 was something like this, and if we find out limit s goes to 0, s into 1 by s into y, like this is the y of t term, s minus 2 whole square by s cube plus 6s square plus 11s plus 6. So this is cancelled. We have 2 by 3. So this is a positive term, right? So here you can guess what? Y1 is positive in this part, and till here y1 dot is also positive. So there you can check at some varying intervals that whether y1 dot is greater than 0, y1 is greater than 0, and what, like compare their values. So then you can see that now we'll get two over under like two zero crossings. First we'll get an overshoot, then we'll get an undershoot, and then the system will settle to that 2 by 3 or whatever, right? So that is the way we can analyze a system. Obviously this system is cubic, and we have some quadratic zeros and stuff, so it becomes difficult to do everything on paper, but for an exam point of view I believe you'll get things that will be manageable. So for now we are taking the help of MATLAB because it helps us visualize properly what and how we are getting. So is it clear till now what we did? Okay, okay. Then this question is done. We'll move on ahead. So at what time in seconds does the trough undershoot occur in the step response of the system? So we have, sorry, s minus 2 whole square, right? This is y of s is equal to this into 1 by s. So now we can use partial fractions, right? Will someone help me with the partial fractions? Okay, we have s minus 2 whole square by s into, and this is s plus 1 into s plus 2 into s plus 3. This is what I seem to have got. If one of you can verify. That's correct? Yeah, okay, then let's move on with the finding the partial fractions. So we'll have a by s plus b by s plus 1 plus c by s plus 2 plus d by s plus 3, and that we'll have to compare everything with s minus 2 whole square. So shall we do it now, or shall I write the answer? Okay, I'll just write it out, you guys can verify as well. So what we get is 2 by 3. Okay, yeah, sure. So this is what I seem to have got. You guys can verify it later. 6, right? So then from here we can find out y of t, right? So what will we have here? U of t 2 by 3 minus 9 by 2 e to the power minus t plus 8 e to the power minus 2t minus 25 by 6 e to the power minus 3t. Right? Does everyone agree with this? Okay. So now again in this question we need some numerical help, but don't worry about an exam point of view. So y of t is this. Now what we want to find out is where does the undershoot occur? So what is an undershoot? We have this kind of thing. So there is kind of a minima kind of thing, right? A local minima. So at that point we know y dot of t will be 0. right? The first derivative will be 0 either at some extrema point. So we want to find all time intervals, all time instances where this first derivative is 0. So perhaps using a calculator or some software, you can find out the time where this is equal to 0, and we get t equals 0.1476 and 0.873, right? So at these two time intervals, we have some extrema, right? So how do we find out where we have the trough undershoot? That we can find out by further finding out y double dash t, that is the double derivative, and plugging in either of these values, 0.1476 and y double dash t, t equals to 0.8739. You will find out that this y double dash of t is greater than 0. So that means that is actually a local minima. So the undershoot occurs at this time instance. Okay. So is the procedure clear? How we solve it is a different thing, but is the procedure like how to do what we want to do? Is that clear? Okay. Okay. So then we move on ahead. So what is the magnitude of system response at the time of trough undershoot? Alright. So we found out that t is equal to some 0.14, what is that? 76. This is the time when we'll get the undershoot. Then we just want to find out y at this time. So that you can again compute as what do we get? Yeah. You can find whatever the terms we had 2 by 3, u of t, and so on. So what I get is minus 0.12085. Okay, is it clear? I mean, this one is a simple one. You just plug in the value and find the from this term, from this term. You can plug in the time value and then find the magnitude that we want to find. Okay. So then what is the steady state output to a unit step reference? So again, we had y of s is equal to limit s goes to, this was 1 by s, the input, into s minus 2 whole square by s cube plus 6s square plus 11s plus 6, right? Then we want to find the steady state values. Limit s goes to 0, s into y of s, that is limit s goes to 0, s into 1 by s to s minus 2 whole square by the terms, right? So what do we get? Everything cancels out, all the s terms goes to 0, only the constants remain, so that is 2 by 3. Is it clear? Okay. So then we move on to a different type of question. Consider this asymptotic body plot as given in the figure. So from origin, we like from the beginning, we have a minus 40 decibel per decade slope. Then as we hit omega 1, we get to a minus 20 dB per decade curve. And then at some point omega 2, we further go back to a 40 minus 40 dB per decade curve. And the open loop transfer function is given by something like this. Two poles at the origin, one 0 at some point and another pole at some point. So this two poles at the origin clearly is visible in this initial minus 40 dB per decade slope, right? Then let's see what we want to find out. So first we want to find out what is the value of A and B. Let's go and look at this question. So since there are two poles at the origin, we'll have a minus 40 dB per decade from the beginning, right? From wherever we are, we'll have a minus 40 dB per decade. Then we see that at this omega 1, we shift to a minus 20 dB per decade. So that means a zero is encountered at that point. So omega 1 is equal to A. Yeah. And B, similarly B, another pole will be encountered at this point, right? Because at this point, omega 2, because here from minus 20 we shift to another minus 40 dB per decade. So omega 2 is equal to B. But we want to find out these values from the data given in this curve. So see that at 1, we have a magnitude of 0 dB, and at omega 1 we have a magnitude of 20 dB. And in this time we drop from 20 dB to 0 dB. That is, we have a change of minus 20 decibels, right? But here the slope itself is minus 20 decibel per decade. So from here to here, we drop from 20 to 0 at a slope of minus 20 decibel per decade. So that means this must be 1 decade, right? Is it correct? Okay. So that means this point is nothing but omega 1 equal to point 1, because that is how a decade is defined. And then similarly, we get to minus 20 with a slope of minus 20 dB per decade from 1 to omega 2. So again, there must be a difference of a decade in these two values. 1 decade. So that means omega 2 is equal to 10. Right. So the original transfer function is k s plus zero point 0.1 by s square into s plus 10. So this is what we have obtained from the information till now. Is it clear till now? Okay. So then we want to find out the value of k. Let's just draw the figure again. We have minus 40 dB at point 1, 20. This is minus 20. And then we go on. Okay. So this is minus 40 dB per decade. This is minus 40 dB per decade. And this middle portion is minus 20 dB per decade. This is 1. This is 10. So now we want to find out the value of k when this is the given transfer function, right? Then what we have is yeah. So how do we find out? We can take one sample point, take this one. So 20. At this point, we have two poles at origin and one zero at the point 1 value. So at this point, we'll consider contributions only due to those things. A zero at point 1 and two poles at origin. Since this is far away, its contribution will be negligible and we can neglect that. So 20 log, and this will be there obviously. So 20 log k, right? Then minus 40 log omega plus 20 log omega is equal to 20. Is that the correct thing? Have I made some mistake here? Okay, yes. Let's just write this k into j omega plus 0.1 by omega square. So 20 log k minus 40 log omega and plus 20 log, right? So what is this? Um, yeah, maybe I'm doing some mistake here. Can you please help me with this? So 20 log k. Just correct me if I'm wrong somewhere. For this we have this term. For this we have this term. And then for this we have this term. Correct. So this I'll equate it to 0 and put all things at omega equal to 0.1. Okay, so let us put it this way: s plus 0.1 equal to 10 into s by 10. Right. So this will be 20 log. Okay, better yet, to avoid all this confusion, what we can do is we can choose a point, say 0.01, right? And find the value here. By the minus 40 dB per decade, we can extrapolate it upwards. Here it was 20 here. So one decade earlier, it would be 60 dB. So at that point, we'll have only from 20 log K and the 40 log omega values. That is equal to 60. So omega equal to, we'll put 0.01. So this thing will become 20 log K minus 40 log 0.01. So 0.01 is 10 to the minus 2. So we'll have this as 80. So 20 log K comes out to be, no, again I'm making some kind of mistake here, I suppose. Okay, 20 log K is just 60 plus, oh, sorry, minus 80. Yeah, okay, this is correct. Then this gives me 20 log K is minus 20, and that is K is 0.1. Okay, sorry for bundling it so many times, but yeah, is it clear what we did here? Yeah, any issues? Yeah, okay. So this is a standard body plot problem. Then, so now consider this system. We have a plant transfer function given by this. We have a controller compensator or controller given by this, and a feedback mechanism, that is, the sensor is accurately measuring this output value. We get it back, and then we put it in a unity feedback configuration. We get this closed loop system. So considering the pole zero cancellation a valid operation, the closed loop system is what? So look at this. The pole of this controller is the zero of this plant, right? So what does that mean? When I multiply these two, these will cancel out. So effectively, GCGP is equal to 4 S plus 5 by S into S plus 4, right? So that is what this question means. Consider that pole zero cancellation a valid operation. So we'll take GCGP is equal to 4 S plus 5 by S into S plus 4. Now I want to find out whether this closed loop transfer function is, I want to comment about its stability. So we'll find GCGP by 1 plus GCGP. So if we do that, here we'll have 4s plus 5. Is it clear? 4s plus 20 by, let's just keep it 4 into s plus 5 by s square plus 8s plus 20. Right. So is this a stable transfer function? What do you think? We can just find out the poles of this directly. No need to use route array. So this is minus 8 plus minus root of b square minus. Right. So this clearly has negative. Sorry. Okay. So we'll have yeah. So here clearly we have a pair of imaginary conjugate poles, and the real part of the poles are negative, minus 4. I think, yeah. So this closed loop system is stable, right? Then now let us consider the next question, right? Uh, Next question, is the system internally stable? Now what do we mean by that? I have this system, some RFS is coming, some controller is there, some plant is there. But here the controller must generate some kind of value, right? To give into the system as some input. So we want to see whether this UFS blows up or not. So for that we'll find out UFS by RFS. That we can find out by UFS is just GCFS into the error term, right? So that means UFS is equal to GCFS into what is the error term? It is 1 by 1 plus GC GP of S. So that means U of S, this will be R of S, sorry, by R of S is equal to GC of S by 1 plus GC of S into GP of S. So in the full closed loop transfer function, we'll have a GP of S here, but for the internal dynamics, all we'll have is this. So now we want to check whether this is stable or not. So GC was what? GC was S plus 5 by S, and GP was zero point 0.5 S minus 2 S plus 4. Yeah, so this we can find out. GCGP is equal to 4 into. So this term we saw last time that it had poles with real part less than 0. This is a pole at origin, but this is a right half plane pole, right? So what that means is the internal dynamics will blow up. All right. So essentially how that will manifest in a physical system is You are giving some reference output. The plant is having some error. That error will be fed back. But since the controller is an unstable system itself, the thing that will be like the controller will get some input, and based on that input, it will keep blowing up the output it is giving. That is the input to the physical system. So that is quite hazardous. So that is why we never go for a pole zero cancellation. Like what we are doing here is we are trying to cancel this S minus 2 and S minus 2. So here we see that the controller is generating an unstable output, which will be harmful for the plant, right? And another issue with this pole zero cancellation is if you do not will never have a completely 100% precise model of some system. It will be like obtained through some kind of approximation, some kind of system identification, something. So we'll never get some system parameter 100% to the actual value. So for that reason, we cannot ever completely eliminate some polar zero that is in the right half plane. So this is not a favorable technique to eliminate undesired poles or zeros. Okay, so is it clear what we did today? Okay. So any doubts in any other question that we did today? Okay. So should I go through the all the procedure or just do the MATLAB simulations? Okay. So look at this that we have a transfer function of this formula, right? Two zeros at some right half plane and the given polynomial. So I'll just share my MATLAB screen. So is my MATLAB screen visible? Okay, let's clear everything. Right. So now let us take g of s as this transfer function. Okay, so this is only the denominator part. Alright, so first let us check what the step output of this system is. So can you see it? So here we can see that the step response of this system with only the poles of the given desired system is something like it starts at 0, it slowly goes up and settles at some steady state value. So if you do some kind of a dominant pole analysis or some kind of that thing, you'll get these values. Alright, then we want to see the next step, that is let's take h as the next transfer function. H is equal to 1 minus 2 comma and 6 6. So we add 1 0 here. So here you see, let's see the step response. So again, here now you can see due to the what we discussed, we'll have that x dot of t minus 2 into x of t. So due to that, the steady state will settle at some negative value, which you can calculate is 0.33 from the final value theorem. But we will have some overshoot due to that initial x dot of t. And then this will come down and settle to its steady state value. Then next, if we take Fs is equal to Df, right? So this is the full transfer function. So let's see the step response. Yeah, is this clear? Like, is it visible? So here we can see uh, we had that thing x double dot of t minus 4x dot t plus 4x of t. So due to that we'll have two zero crossings. One at some this value. So if you remember, we calculated it was somewhere around 0.8374 something, and then another somewhere here. Sorry. This is this is the trough undershoot. Okay, this is the peak. Yeah. So this is how we can find out the things in the system. All right. So is it clear? Okay. Okay. So with that, maybe we'll stop for today. Thank you for attending the session.